Welcome to Future Talk. On today's program, we're going to talk about the search for exoplanets, which are planets from other solar systems. In 2009, NASA launched the Kepler mission to look for exoplanets, and it actually found quite a few of them. But when Kepler's stabilizers failed, it was no longer able to do its work, and the mission was presumed dead. But an ingenious fix brought it back to life, and now, operating as the K2 mission, it's doing better science than ever before. My guests are three astrophysicists from the Kepler K2 mission, all of them working at NASA's Ames Research Center. On my immediate right is Jessie Dotson, the project scientist for the mission. On my far right is Geert Barantsen, whose work deals with the data generated by the mission. And on my left is Christina Hedges, a support scientist for the mission. And I would like to thank each and every one of you for coming here today.
Thank you. Thank you so much for inviting us.
Well, Jessie, what exactly is the goal of the Kepler/K2 mission? What's it really looking for?
So Kepler was designed and built to do one thing really, really well, and that was to find planets around other stars. And along the way, we found a lot of other fascinating results, but that was really what we were launched to do, is to find planets around other stars, understand how common they are, understand, are there small planets, are there large, how common are large planets, and just try to get a census of what's out there.
Now, how does it do that? Doesn't the light of the star prevent you from seeing the planets?
So it does, absolutely, and we use what's called the transit method. And so I think we have a video on that, which is a great way to explain how this works. Yeah, I think we do.
Let's go ahead and see that video that illustrates the transit method.
So what happens is the planet passes in between us and its host star, and we monitor the brightness of the star very, very carefully, and the star gets a little bit fainter when the planet passes in between us and the star. And so you can see on the right-hand side that kind of U-shaped dip, and those green dots are kind of like what our raw data looks like, and that's how we tease out if a planet is going around a star in the distance.
And what information can you extract from that? Let's say a planet goes around at periodic intervals, there's a dimness. So what can you figure out just from that alone?
So what we can figure out from just that alone is we can figure out the size of the planet relative to the size of the star. And we have other ways to estimate the size of the star, so that lets us estimate the size of the planet. Also, by paying attention to how frequently that dimming occurs, we get an idea essentially of how long it takes for that planet to go around the star, or how long that planet's year is.
Would that tell you how far the planet is from the sun and maybe how hot it is?
It does tell you how far away from the sun the planet is, and because we can measure how hot the star is, we can estimate how hot the planet is.
Now, I understand that the Kepler mission seemed to fail because the stabilizers that enabled it to have a steady gaze were no longer working, but it was resuscitated somehow. What was the fix that enabled it to continue after the stabilizers went out?
So we have a model which
let's see that.
And so this is what our spacecraft looks like. The light comes in this end. There's a mirror in here. There actually is a mirror in the model. And our camera is in there. These are our solar panels, and all this doodads down here are kind of what controls the spacecraft, dishes to let us talk back to Earth. And what failed is actually what we call reaction wheels. And you need 3 reaction wheels to point to hold, steady in a particular direction. We launched with 4 reaction wheels, and 2 of them failed. And at that point, we really could no longer operate the way we used to. And being able to point very precisely was really important to be able to measure these tiny changes in brightness of the star. Luckily for us, some extremely clever spacecraft control engineers at Ball Aerospace, who built the spacecraft for us, figured out that because our spacecraft is very symmetrical, and because of which reaction wheels failed, we could essentially point this symmetric axis of our solar panels towards the sun, and then the solar pressure from the sun basically allows us to control around that third direction. And it's kind of like when you see a river kayaker, they can put the nose of the boat right upstream, and if they get it pointed exactly right, they can stay there a long time and stay pointed very precisely without much effort. As soon as they go off a little bit, they go whoosh and whoosh around.
Is the solar pressure steady? Is it predictable, always the same?
It is. It is. And so that method has allowed us to continue to operate Kepler in the Kepler spacecraft in a very precise manner. The one hitch is that during the main mission, we looked at the same part of the sky continuously. We took a brightness measurement of 150,000 stars every 30 minutes. And the reason we wanted to look at the same stars for that long is we wanted to find planets with years as long as ours. But because we have to keep in this orientation, we could no longer look at the same part of the sky. We now have to look at a different part of the sky every approximately 80 days so we can maintain this exquisite balance with the solar pressure. And that's both been we were very disappointed when we couldn't keep looking at the same part of the sky. We wanted to find planets with even longer years than ours. But it's actually been a bit of a blessing, because what it means is we've been able to take these kinds of high precision measurements in a variety of different places across our galaxy, which means that we have a wider variety of objects to look at. And so we've been learning new things that way.
Is it still based on the idea of staring at things, but you're just looking at a different area now?
Exactly.
Okay. We actually have some slides which show some of the stuff that the mission has discovered. Can we see the first slide, please?
So this first slide shows the planets that were known before Kepler launched in 2009. And what we're showing is the orbital period, or essentially how long the year is for these planets on the x-axis. And on the y-axis, we're showing the size of the planets relative to Earth. And for reference there, we've drawn a line at 1, and you can see on the left-hand side there's Earth. Those are, anything around that line is the same size as Earth. We also have a line drawn around Neptune, and up there at Jupiter, which is a little bit more than 10 times the size of Earth. And so before Kepler launched, we knew of about 326 planets. All of them tended to be quite a bit larger than Earth, generally around Jupiter size, and that has a lot to do with the methods we had to find exoplanets before Kepler.
Is that because smaller planets are harder to see?
Absolutely.
Okay, can we see the next slide, please?
Now this next slide, these are the number of exoplanets we knew as of December this year, or about a month ago. And we now know of over 3,500 confirmed exoplanets, and 2,500 of those were discovered by Kepler. And you can see we've started to fill in planets in the smaller regions. We are finding some Earth-sized planets, some Neptune-sized planets. Those ones in between Earth and Neptune are just fascinating to me because we have found a lot of them, and there's nothing like that in our solar system. And so we have no local analogs.
We're starting to think that most stars have planets around them.
At this point, one of our big results from Kepler is we now believe there are more planets than stars in our galaxy.
Okay, let's see the next slide, please.
Okay, so this is one of the systems that was discovered relatively recently. This was actually found in the original Kepler data. This was the 4 years we took in the one field of view. And so that we stopped taking that data in 2013, but people are still combing through that data to find new results. And this is a really interesting system that we announced in December. Kepler 90 was actually found using artificial intelligence. It was a collaboration in between a NASA Sagan fellow named Andrew Vandenberg at the University of Texas and a Google engineer named Chris Chalou, who's an expert in artificial intelligence. But they were able to use that method to find the 8th planet in Kepler 90. So the Kepler 90 system is now tied for our own solar system with 8 planets.
So does that mean that if we apply the same artificial intelligence to other data, we might find more of the same?
Absolutely. The search for planets in the Kepler data is very much still ongoing because we observed so many stars, about 500,000 now, that it's actually a bit too much for astronomers to look at individually. And so we're both developing new algorithms in collaboration with Google, but also with astronomers and indeed citizen scientists, just volunteers in the public, to continue the discoveries. And we expect that we will have another decade of discoveries ahead of us from this gold mine of data.
Is it mostly going to be done ultimately by artificial intelligence, so humans can't even begin to compete in analyzing this type of data?
You know, algorithms can do a lot. We're seeing this in our daily life. Some algorithms drive cars, but the human brain is still an exceptional instrument. There's I think 100 trillion synapses in the brain, which is still 10,000 times more than there are transistors in CPU chips. And what we see is that while algorithms are very good at doing what humans tell them to do, finding a certain planet or finding a certain type of exotic star, what they're not good at is finding exotic objects or surprises in the data. And so we need humans still to comb through all those 500,000 stars that we carefully observed to check for any surprises. And indeed, many have been found.
And I would even go one step further, which is when the machines, the artificial intelligence relies on training sets, okay? And so the reason this method worked is humans had gone through the Kepler data and figured out what does it look like when there's a true planet going through? What does it look like when there's something that looks like a planet but isn't? And so Chris Chalou and Andrew Vandenberg used what the humans had found to train their algorithm, and then their algorithm was able to find more things. And so we need to rely on humans to find the original discoveries, and then we can train the machine learning to go and find the rest.
Well, let's take a look at the next slide. We have a few more slides. Let's see the next one, please. Ooh, habitable zone planets. What does that tell us?
So this graph that we've got in front of us, we're looking at the energy that the planet receives. So Jessie before was talking about how planets, we can determine the temperature that they are based on the period. So they have a year that takes some amount of time for them to go around that host star. And then the further away they are, the cooler they are, the closer they are, the hotter they are. And so when you have a very small planet, you can actually be very, very close to that host star and still be fairly cool. So if you were around a small star, you can have a temperature of roughly water, liquid water kind of temperature, somewhere around 20 or so days. So your year will take 20 days, but you'll still be fairly temperate.
So does that mean that the definition of a habitable planet is one where water can exist in liquid form, basically?
So there are a couple of definitions of habitable zone, but that is one simple definition of a habitable zone, which is we assume that life needs liquid water, all life on Earth needs liquid water. And so we can define a simple habitable zone as what separation do you need to be from your host star in order to have a temperature where liquid water can exist.
Okay. Are there any other things we look for to determine if a planet could be habitable? Can you detect chemicals in the atmosphere?
So we absolutely can detect chemicals in the atmosphere of exoplanets. So when we have this exoplanet transit in front of the star, when you have an atmosphere around that planet, some of the stellar light actually transmits through that atmosphere and interacts with the molecules that are in the atmosphere. And so in certain wavelengths, those molecules can make that atmosphere opaque.
Now, can Kepler determine that, or do you need some other type of instrument like the Hubble Space Telescope to look for that?
So that's exactly right. Kepler is very good at providing a catalog of incredibly exciting exoplanets and a range of sizes, as Jessie's already said, with lots of different types of planets, Jupiters and Earths and something in between. But then we need an instrument such as the Hubble Space Telescope to zoom in and take a closer look and look at the atmosphere.
So Kepler can say, this is a good candidate over here. Why don't you take a closer look with your equipment and find out something that I can't?
That's exactly right.
So all this stuff is kind of working together.
Absolutely.
Can we see the next slide, please? Okay, this is exoplanet populations. What does that refer to? Types of planets?
That's exactly right. For me, this is a very important graphic because for me, there are two key results from Kepler. One is what Jessie said. We now know that there are more planets than stars in our galaxy. And that's fundamental. That changed the way I look at the night sky because there are 100 billion stars that we know of in our galaxy. And that means there's hundreds of billions of planets. Fascinating. Now, this chart goes into more detail. And we've now moved on from establishing that planets are common into trying to understand what those planets are like. So here on the chart, we see the distance of a planet from its host star on the x-axis. And on the other axis, we see the size relative to the Earth. And what's fascinating here is that planets, a bit like humans, come in all sizes. Some are small, some are large, some are cold, some are warm. the diversity of planets is a discovery of Kepler, because maybe 20 years ago, astronomers thought they had figured it all out. We had the rocky planets in our solar system, Mercury, Venus, Earth, and Mars, close to the star where it's warm. So perhaps the ices and the volatiles would evaporate quickly. And then we have Jupiter, Saturn, Uranus, Neptune in the outer solar system where it's colder, so you keep those gases and ices. But what we see now in the data of Kepler is that both these giant planets and these rocky worlds come in all sizes at all positions relative to their host star. And that's a real surprise that astronomers are still trying to explain.
Now, do we think that most planets are formed at the same time as the star, condensing from the same ball of gas, or maybe planets captured? Maybe you have orphan planets just floating around unattached and they get pulled into a solar system somewhere.
So we think it takes a few million years for planets to form from this big ball of dust and gas that collapses to form a star and its planets. Now, our models struggle to explain how we can, for example, form a big Jupiter planet in an orbit just 4 days around its star, and yet we see those planets. Another aspect that's surprising is that the most common planet we found is something called a super-Earth. That's a planet about 2 or 3 times the size of our planet. We think these are water worlds because they will have a very big layer of water, an atmosphere of water around them. And we don't see that planet in our own solar system, and that's a bit surprising. And so we're now just starting to get our head around what these planets are like.
Now, is the ultimate goal here to see what planets are like, or to see if we can find intelligent life on other planets?
I think the answer is yes, but I'm an astrophysicist, right? And I love the idea of just understanding the variety of planets that are out there, and that there are multi-planet systems where all the planets are packed in, you have 6 planets packed in closer than the Earth is around our sun. Understanding that there are ocean worlds, lava worlds. I just find that fascinating. Now, of course, it is really exciting to think about, could there be life on one of those planets? And that is one of the questions that drives missions like Kepler and some of the follow-on missions like TESS. But, we are just one step along that quest to discover whether or not there's life.
Well, since you mentioned TESS, tell me something about that, because this is a new mission which I believe is going to be launched a couple of months from now as the successor to Kepler.
Yes, it is a bit of a successor to Kepler, in that what TESS is going to do is going to find planets using the transit method. But what it is going to do, rather than trying to do a census of planets, its real goal is to find those planets that are really amenable to doing subsequent observations, to measure the atmospheres with Hubble or with the upcoming James Webb Space Telescope. And so it's going to be looking for planets around bright stars all over the sky.
So it'll be looking for candidate planets, and then it'll follow up with, say, the Webb telescope, which hasn't been put up there yet, but is well along in its development?
Yep, exactly.
Okay. So it looks like things are going pretty well. We're learning a lot. Would you say that this field is growing exponentially like certain other areas of science right now? Is it like you go to the lab every day and you're making new exciting discoveries every day?
Absolutely. 20 years ago, we discovered the first exoplanet around the Sun-like star. That was one of these hot Jupiters on a very short period, which is easy to find. And maybe 20 years ago, we honestly did not know that planets were common. In fact, there were theories that perhaps planets only formed when two stars collided, and then maybe in the debris from such a collision, you would get planets. We now know that is absolutely wrong, because we now know there's planets everywhere.
What are the limiting factors as far as research? What are the most important technical problems you have to solve in order to get still better observations?
Oh my goodness, that's a whole other hour show. And making the next steps in scientific discovery, it's a little bit of two things move forward at once. You ask the next question, and you develop the next technology to help you answer that question. And then sometimes you tune your questions a little bit, because it's what the technology that's available allows you to answer. We talked about trying to understand if some of these exoplanets are habitable, and Christina mentioned about trying to understand the molecules that are in their atmosphere. Ideally, we would love to be able to say, look at the atmospheres and say, this is an atmosphere that has life, that has demonstrated life. We don't have the tools to do that yet. We don't have the sensitivity to do that yet. We can find water, we can find methane. And so, you know, we need instruments with larger collecting areas, high spectral resolution. Ideally, we'd like to be able to actually image planets around other stars, and particularly image planets in the habitable zone around other stars. And NASA has a whole effort to develop the technology to allow us to do that.
I think we have 1 or 2 slides left. Can we see the next slide, please? Okay, so this is Kepler and K2, how they work differently.
Yeah, so this is one of my favorite pictures, actually, because what you're seeing on the left-hand side is kind of representing the 4 years we spent looking at the primary Kepler field, which is where the version of Kepler on the left-hand side is pointing, that one field, just looking at the tip of the Cygnus the Swan's wing. So we looked in that field for 4 years. Since 2014, we've actually been looking at, you see all those little funky, squished looking boxes. Each one of those represents a different part of the galaxy that we've looked at.
That's a different target area for the device?
Yes, exactly.
Now, do you mostly want to aim at the center of the galaxy because presumably that's where most of the stars are?
Actually, we want to aim at all parts of our galaxy. One of the big science questions that K2, the extended Kepler mission, is answering right now is there a dependency on the number of planets as a function of the position in the galaxy? You know, we are starting to see evidence that some parts of our galaxy are older than other parts. We're starting to see evidence that the chemical composition is different. And so the next question is, you know, is life perhaps more common in other parts of our galaxy because the conditions, i.e. the existence of planets, might be more common in certain parts of the galaxy.
Well, what does it mean that one part of the galaxy is older than another? Does that mean that the stars were born at a different time? So stars are born, right? They're not just always there. Out of this amorphous cloud, bits of it condense and they come together as a star through gravity?
Yeah, that's correct. Stars have a life cycle. And in fact, an interesting story to tell there is that stars die as well. They die in so-called supernova explosions. And in some of these fields that we have been pointing at, we have a lot of galaxies, like galaxies outside of our own Milky Way galaxy. And what we're doing right now, this very moment with Kepler, actually, is looking at 10,000 galaxies. We're monitoring them, and we're seeing explosions go off in those stars, supernova explosions. We just had 9 of those explosions in the last month. And this is exquisite data because Kepler is such an amazing instrument. And so we are learning not just about how exoplanets differ in those different parts of the galaxy, we're actually also looking outside of our galaxy now and studying these very powerful explosions, which are revealing new physics.
Now,
and the cool thing we can do with Kepler to look at these supernova explosions is people have been studying supernova for as long as we've known they existed. And when you find, the way you find supernovas, you look at a galaxy, then you come back a couple nights later and you look again, and if something all of a sudden got brighter, you know a supernova is there. But with Kepler, because we are staring at these 10,000 galaxies continuously for 80 days, when a supernova goes off, we get to see that explosion from the very beginning. And so I think of it kind of like, you know when you go and you see a big like shoot 'em up movie, and if you happen to be out of the room getting popcorn when the explosion starts, you come back, all you see is stuff flying everywhere, you don't know what exploded. With Kepler, because we're seeing the beginning of the explosion, we can start to get information about how the explosion starts.
and presumably when it explodes, any planets that might have been going around it would be incinerated, I guess.
Absolutely, and one of the unexpected but really cool things that we found with K2 is we found a planet disintegrating around a white dwarf. A white dwarf is one of the end stages of stars. And we have actually found a planet that is transiting the white dwarf, and because of the shape of the transit and the metals are basically the elements that we see in the star's spectrum, we know that this planet is being torn apart and raining into the white dwarf. So we've seen actually the end of a solar system. We are watching the end of a solar system with K2.
So by looking at so many solar systems at the same time, I guess you could draw a timeline, a typical lifestyle, see solar systems at each stage of their development.
And that's actually one of the great benefits of K2, because we can look at all of these different fields at different ages. We're trying to probe into the different life stages. We've recently been able to find a very young planet in a very young association called Upper Scorpius. And it's allowing us to really sort of peer into the very beginning stages of how these planets are forming. We can also see the stars that still have these disks. As you get this cloud that collapses down, they actually maintain the disks that the planets form from, and so we're able to see those in some of the young stars.
So how old is our solar system? Are we a young solar system or a middle-aged solar system? Do we know?
We're about 5 billion years old, which is not particularly old, it's not particularly young. In many ways, the Sun is a very boring, ordinary star with what we thought was a very boring, ordinary planet of a middle age. And I think for me personally, the reason Kepler is so fascinating is that we have now been able to travel to those other solar systems to compare. It's a bit like when you travel to a foreign country and you find out that cars drive on the left side of the road, or suddenly your coffee is very small and very intense.
And there's no to-go cups.
And there's no to-go cups. And we've now been able to sort of start to understand which things are universal, because when you go to a foreign country, people still eat and sleep in similar ways. But we're also starting to see which things are different. And that's how we put ourselves into perspective and how we give context to our existence. And that's what fascinates me about the Kepler mission and what it has taught us.
We just have about half a minute left. Any final comments before we wrap?
You know, I just want to, thank you, Marty, for giving us the opportunity to come and talk to you about this. We love what we do, and thank you for giving us the opportunity to just share how exciting these results are and how exciting this mission is.
Okay, and thank you all for coming. Had a great time. I think we learned a lot. I've been speaking with Jessie, Geert, and Christina from NASA Ames, talking about Kepler K2. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman, and we'll see you next time.